Welcome back to Finding All Rational Roots of a Polynomial Function, the best video ever. Okay, so in part 2 here, we're going to look at testing the roots that we got from our list, right? Our possible list here that we got from the rational roots test. Okay, we're going to test these using a process known as synthetic division. There's another thing called polynomial long division, which is really tedious and a pain in the butt. And so somebody came up with synthetic division, right, which is a little easier to use and a little cleaner process, and not quite so time and space intensive. So in order to do this, again, this is very simple, right? It just might take some time. So we're going to set up our equation here. We have our original equation, x to the fifth minus 6x to the fourth plus 10x to the third minus 11x plus 6. And we're going to basically write down only the coefficients of each term. So we have a 1, negative 6, 10. We also have a missing term here. We don't have an x squared term. So what we're going to need to do here is have a 0 coefficient representing that x squared term. And we have negative 11 representing the x term, and then finally a 6 is the constant term. So we're just going to write down those numbers by themselves. 1, negative 6, 10. Do not forget the 0 representing the x squared term, negative 11, and 6. As you can see here, we're working our way down. We have the 5th degree, 4th degree, 3rd degree, 2nd degree, which is 0, right? It's gone. 1st degree, and constant term. Okay, so it's very important to put this in descending order from greatest power. Okay, so now that we've written these down, we're going to make a little box. Okay, it's important to make the box right. This is a lot like long division in some ways. We're going to make a box here and a line across. Notice that there's space underneath the numbers. There's space for another row of numbers there. Now, we have our list of possible roots. We're going to test them one at a time. I always start with the smallest number, the easiest one to work with. You can see here we have a possible 0, right, a positive 1. That's a very easy number to work with. So we're going to take that positive 1 from our list of potential zeros, right, we're going to put it right outside this box. Okay, as if we were almost doing long division. Now, we're going to take this and the first step is to carry down the first one. Okay, so we get 1 underneath. Now we're going to take this and multiply the outside one by the bottom one and carry it to here. So multiply, and this goes here. So 1 times 1 is obviously 1, and we get a 1 there. And now we add these two together. Negative 6 and 1 is negative 5, right? So we get negative 5 there. Now we repeat the process. We multiply 1, the outside 1, right, by negative 5 and get negative 5. Add, we get 5. Now we multiply the 1 by 5, right? So every time we're multiplying by that outside 1, we get 5, right? We get 0 plus 5 is 5. 1 times 5 is 5 again. We get negative 6. 1 times negative 6 is negative 6. We add those two together, 6 and negative 6, to get 0. Now this is exactly what we want to happen. Right? It's great to get a final answer here of 0, the last column. That means that this 1 is indeed a root of this function. If we get another number here that's not 0, we have what's called a remainder. Right? And that means this is not a 0. So getting a 0 is awesome here. Right? Getting a 0 in this last column is exactly what we want to have happen. Okay? So that tells us that 1 is indeed a 0. Okay, so we're going to make a little list here of zeros. We're going to circle positive 1 here. Okay, that gives me positive 1 is a 0. Now, here's the tricky part. We know that it's possible to have multiple zeros. Okay, we can have more than one 0, right, and we get a bounce, or in some cases we get a slowdown. Okay, so what we're going to do here is test the same 0 again. Right? So I'm going to go ahead and draw another box. The nice part here is I don't have to start over, because I've already factored out that x plus 1 linear term, or sorry, x minus 1 linear term. All right, I can just take this and draw another box over here. I've created a new polynomial, which is really a 4th degree polynomial now, right, rather than a 5th. Okay? So I'm going to throw that 1 outside again, right, because I'm testing 1 twice to make sure it's not a double 0. So I pull down this 1. 1 times 1 is 1. Negative 5 times 1 is negative 4. 1 times negative 4 is negative 4. This is 1. Right? 1 times 1 is 1. 5 plus 1 is 6. 1 times 6 is 6. 6 times 6 is 0. And once again, we've reached our 0. So that tells us that 1 is another root of this function. In other words, it's a double 0 here. So it's a good thing we tested it twice. Now we can continue this process, right, by checking the next number. I'm going to use negative 1, right, because it's a small number. So again, I'm going to start from here and work my way down, right, with negative 1 on the outside rather than positive 1. Okay, so this is my next one. I could test 1 again. It's unlikely there's a triple 0, but you might want to test it again and see what happens. Okay, so here I go down. We get 1. Okay, negative 1 times 1 is negative 1. This is negative 5. This is 5. This is 6. This is negative 6. And this is 0. All right, we're doing great. Right, we've reached yet another 0 remainder, right, which means that this is indeed a factor, right, which means that this is 0. So negative 1 is also 0 in this function. At this point, if we look at this, we have 3 numbers left, 1, negative 5, and 6, which means this is actually a second-degree polynomial or a quadratic. This represents x squared minus 5x plus 6. When you get down to 3 numbers here, in other words, you have a quadratic term, right? That means you can use the quadratic function or you can just factor however you want, okay? Which is great. It gives you your zeros in a much quicker way than having to work this through. So if you get a quadratic, if you get 3 numbers left over, use the quadratic formula. You have your calculator to do that, or you can factor. In this case, it's pretty obvious that the factors here, we have x minus 3 and x minus 2, which of course gives us a factor of x equals 3 and x equals 2. So if we put them all together, we have 5 roots. We have a double root at 1, we have negative 1, we have 3, and we have 2. So all the roots we tested our roots. We know we don't have any more than 5. And you'll notice, right, we have 4 positive roots, 1, 1, 3, 2. We have 1 negative root, just negative 1, which is exactly what the Descartes' rule of signs told us. So all roots are 1, 1, 2, 3, and negative 1. Okay? So that's great. We're done. Now, if we look at the graph of this function, right, we could actually graph it using these zeros, or at least sketch a graph, right? We know that it's going to bounce at positive 1, right? And we have a couple other zeros along the way. We're going to have turns in between those zeros. Right, but we can use our calculator to look at this function. Right, we have it, I have already put it in there. I'm just going to zoom standard. And you can see it appears to cross at negative 1. Looks like it bounces at 1, goes back through the x-axis at 2, and again at 3. So it's exactly what we predicted. We were able to come up with, right, basically a behavior pattern for this graph just by finding the rational zeros. Now this gets more complicated, right, if you have a longer polynomial or a different leading coefficient than 1, or sometimes because then you'll end up with fractional zeros you have to test. Right, but again, the process is exactly the same every single time. Those 5 steps are going to give you the possible, all the zeros of this function. Okay, I hope that makes sense. If you have any questions, you can ask me on Facebook. All right, good luck.